Hello everyone, I am Mritunjay Pandey, BTech 4th year student of Civil Engineering at Faculty of Engineering and Technology, University of Lucknow. My seminar topic is Biofiltration of Air. This is my table of content which include following topic that is to be discussed are given below. Common air pollutant, need of biofiltration, introduction, history of biofilter, application, component of biofilter unit, microorganism in biofiltration, mechanism of biofilter, parameter that need to be maintained, types of biofilter, benefit of biofiltration, biofiltration application, challenge and limitation, case studies, environmental impact, future trend, conclusion. Common air pollutant. Common air pollutant are those pollutants which pollute our environment. First is particulate matter, fine particles of solid or liquid suspended in the air. Particulate matter are classified as particle size less than equal to 2.5 micrometers or PM 2.5 and particle size less than equal to 10 micrometer or PM 10. Source of particulate matter are various harmful gases from industries, combustion of diesel and petrol in vehicle, and natural events like dust and storm. Second is gaseous pollutant, gases that can harm human health and the environment. Gaseous pollutant include sulfur dioxide, nitrogen oxide, carbon monoxide, and ozone. Source of gaseous pollutant are harmful gases from industries. Vehicle produce huge quantity of carbon monoxide, sulfur dioxide are produced by burning of fossil fuel in power plant. Third is volatile organic compound, organic chemical that can easily evaporate into the air. Sources include industrial process, vehicle emission and household product contribute to the formation of ground level ozone and smoke. Fourth is greenhouse gases. Greenhouse gases are responsible for global warming and climate change. Main greenhouse gases are carbon dioxide, methane, and nitrous oxide. Major sources included fossil fuel combustion, deforestation, and agriculture. Toxic air pollutant. Hazardous air pollutants. Chemical known to have severe health and environmental impact. Example: lead, benzene, mercury, and formaldehyde. Need of biofiltration. The shifting precipitation pattern coupled with higher evaporation rate have significantly contributed to the growing frequency of drought, which in turn bears severe implications for both food security and water resources of the country. India is the second most populous country in the world, is recognized as hotspot for aerosol loading where PM 2.5 exposure was observed to increase rapidly over the past decade. India was the third largest emitter of carbon dioxide by volume in 2020 as per UN emission gas report. The concentration of particulate matter between 60 to 90 microgram per meter cube included the Rajasthan and Punjab region. The concentration of particulate matter between 30 to 60 microgram per meter cube included Tamil Nadu and Andhra Pradesh region. The particulate matter concentration less than 30 microgram per meter cube included Ladakh, Arunachal Pradesh and Nagaland region. What is biofiltration? Biofiltration is a biotechnology process used to treat air contaminated with volatile organic compound, odorous compound and other pollutant. It relies on microorganisms, typically bacteria and fungi, to degrade and convert these pollutants into harmless byproducts like carbon dioxide and water. History of biofilter. The first biological method were proposed to treat odorous emission in 1923. Next, 1955 biological method were applied to treat odorous emission in low concentration in Germany. Then 1960 biofiltration was used for the treatment of gaseous pollutant both in Germany and US. 1970 biofiltration is used with high success in Germany. 1980 biofiltration is used for the treatment of toxic emission and volatile organic compound from industry. 1919, there are more than 500 biofilters operating both in Germany and Netherlands, and it is widely spread in US. Component of biofilter unit: filter bed media. Filter bed media included compost, wood chips, peat, synthetic material, or combination of these for the habitat of microorganisms. Microorganisms such as bacteria, fungi, and sometimes algae are the active agent in biofiltration. They metabolize and biodegrade the pollutant present in the air and converting them into less harmful substance. Moisture control system: maintaining the right moisture can increase the rate of growth of microorganisms in the habitat. Air distribution system: proper air is required for the biodegrade and metabolize the pollutant present in air. Control and biofilter housing: biodegrade and metabolize of pollutant present in air by microorganisms create a bad smell for residential area. So proper odor control system is stabilized like carbon bed method to reduce odorous emission. Exhaust system: after passing through the biofilter, the treated air is discharged into the atmosphere. An exhaust system ensures that the purified air is safely released.
Microorganisms in biofiltration. Fungi. Fungi are also important in biofilter, particularly for the degradation of complex organic compound. Certain fungi such as trichoderm and aspergillus can be used in biofilter systems. Archaea. Some biofilter units may contain archaea, which are microorganisms that can thrive in extreme conditions. Archaea play a role in the removal of specific contaminants like methane and ammonia. Algae. In biofilter unit designed for water treatment, algae can be used to absorb and metabolize nutrients like nitrogen and phosphorus. Algae are particularly effective in treating wastewater. Protozoa. Protozoa are single-celled microorganisms that can prey on bacteria and help maintain the microbial balance in biofilter. They contribute to the removal of organic matter and biomass control. Bacteria. Bacteria are the primarily microorganisms used in biofilter. They can degrade a wide range of organic compounds and pollutant. Common bacterial species used in biofilter include Pseudomonas, Bacillus, and Nitrosomonas. Mechanism of biofilter. And first is introduction of polluted air. The contaminated air containing pollutant is introduced into the biofilter through an air distribution system, typically at the base of filter bed. Second is adsorption. Upon entering the biofilter, some pollutant may be initially adsorbed onto the surface of filter media. This physical process can help capture certain volatile organic compound and particulate matter. Third is microbial attachment. The polluted air moves through the filter bed media, which provide a porous structure with a high surface area. Microorganisms including bacteria and fungi attach to the media surface and begin to colonize. Fourth is metabolic activity. The microorganisms present in the filter bed are responsible for the primary pollutant removal mechanism. They metabolize and biodegrade the pollutant by breaking them down into simpler, less harmful compounds. This metabolic process often involves enzymatic reactions. Fifth is nutrient supply. Microorganisms require nutrients to sustain their growth and metabolic activity. Nutrient solutions containing nitrogen, phosphorus, and micronutrients are introduced into the filter bed to support the microbial population. 6 is moisture control. 6 is moisture control. Maintaining an appropriate moisture level within the filter bed is critical for microbial activity. The moisture control system ensures that the filter media remains sufficiently damp to support microbial life and pollutant removal. Seventh is biological reaction. Within the biofilter, a series of biochemical reactions occur as a microorganism consume and convert pollutant into carbon dioxide, water, and other harmless byproducts. The specific reaction depends on the type of pollutant and the microbial community present. Eighth is pollutant removal. As the polluted air passes through the filter bed, the microorganisms efficiently remove and degrade the contaminant. This results in the reduction in the concentration of pollutant in the air stream. How does biofilter work? The polluted air passes to the pre-filter where the organic compounds are adsorbed on the surface of pre-filter, and then the polluted air passes to the micro HEPA filter. The micro HEPA filter absorbs the size of pollutant which are less than 0.3 micrometer. Micro HEPA filter is a high efficiency particulate adsorber filter. Then this polluted air passes to the VOC filter. VOC volatile organic compound are adsorbed in this filter, and then clean air is passed through environment. Parameters that need to be maintained. First is moisture content. Optimum moisture content is 20 to 60% for microbial activity. pH. Neutral pH between 6 to 8 is required for the microbial activity. Temperature. Maintaining an optimal temperature of 30 to 40 degrees Celsius. Nutrient level. Microorganisms require essential nutrients like carbon, nitrogen, phosphorus. Monitoring nutrient level and ensuring an appropriate balance is important for microbial growth and pollutant degradation. The oxygen, nitrogen and phosphorus ratio is estimated is 100:5:1. Oxygen level. Aerobic microorganisms require oxygen for their metabolic process. Ensure that the biofilter has adequate oxygen level, which may involve proper aeration. Types of biofilters. First is trickling biofilter. Trickling biofilter, also known as packed bed biofilter, consists of bed of inert packing material such as wood, chips, peat or plastic media, through which contaminated air is passed. Microorganisms colonize the surface of the packing material, forming a biofilm. Air flows through the biofilm and pollutant and biologically degrade. These biofilters are relatively simple to construct and are suitable for treating a wide range of contaminants. Second is granule biofilter. Granule biofilter use small granule media like sand, activated carbon or other porous material as the filter media. Microorganisms attach to the media surface forming a biofilter. This type of biofilter is well suited for high flow rate and can handle high pollutant concentration. Third is packed biofilters. Packed biofilters are similar to trickling biofilter but use a broader range of media including plastic beds or foam cubes. These filters provide a large surface area for microbial growth and are often used for treating odorous compounds. Fourth is fluidized bed biofilters. Fluidized bed biofilters suspend the filter media in an upward flow of air. The media particles are kept in a state of suspension, allowing for better contact between microorganisms and pollutant. This design is effective for treating high concentration of contaminants. Fifth is rotating biological contractor (RBC). RBC is biofilter with a series of rotating discs partially submerged in wastewater or air treatment system. Microorganisms grow on the disc as they rotate through the air stream. Contaminants are removed. RBC are particularly effective in treating volatile organic compound. 6 is membrane biofilter. Membrane biofilter combines biological treatment with membrane filtration. They use a membrane barrier to separate microorganisms from the air stream while allowing treated air to pass through. This design is effective for treating contaminants that might harm microorganisms in additional biofilter. Seventh is aerated biofilter. In aerated biofilter, air is introduced into the biofilter to provide oxygen to the microorganism, promoting aerobic degradation of pollutants. These biofilters are suitable for treating volatile organic compound and other organic compound. Benefits of biofiltration. First is environment friendly. Biofiltration is a sustainable chemical free method for air purification. Cost effective. Operating and maintenance costs are generally lower compared to other air treatment technology. Versatility. Biofilter can be tailored to target specific pollutant, making them adaptable to different applications. Odor control. Effective in reducing and eliminating odor associated with industrial process. Biofiltration application. Odor control. Biofilters are commonly used to control and remove odorous compounds emitted from the industrial facility, wastewater treatment plants, composting facility, and agriculture operation. Microorganisms in the biofilter break down the odorous compound, reducing or eliminating unpleasant smells. Volatile organic compound. Removal biofiltration is effective in removing volatile organic compounds such as benzene, toluene, xylene, and formaldehyde from indoor and industrial air. It is widely used in the printing, painting, and chemical manufacturing industry to meet air quality regulation. Indoor air quality. Biofiltration can be applied in indoor environment to improve air quality by removing indoor air pollutants like formaldehyde, ammonia, and other volatile organic compounds. It is used in homes, office, and commercial buildings to provide cleaner and healthier air. Air pollution control. Biofilter can be employed to reduce air pollution from various sources including industrial process, waste incineration, and exhaust gases from vehicles and equipment. They help in reducing emission of pollutants like sulfur compound, nitrogen oxide, and particulate matter. Greenhouse gas reduction. Biofiltration can be used to capture and reduce greenhouse gases such as methane, carbon dioxide from sources like landfill, agriculture operation, and wastewater treatment facility. Microbial activity in the biofilter can convert methane into carbon dioxide, which is less potent as a green. Bioremediation of contaminated air. Biofilter can be employed to treat air contaminated with harmful substances such as volatile, pesticide, or chemical spills in controlled environment. Microorganisms in the biofilter can break down and degrade these contaminants. Indoor plants are for air quality. Some indoor plants such as snake plant and peace lilies have been used to improve indoor air quality by absorbing and metabolizing indoor pollutants. These plants act as a natural biofilter and are often used in homes and offices. Green building design. Biofilter system can be integrated into the design of green building to provide natural air purification and improve overall indoor environment quality. Bioenergy production. In some applications, biofilter can be used to capture and concentrate methane emission from sources like wastewater treatment plant. This capture methane and can they be used as a renewable source of energy. Challenge and limitations. High initial cost. The installation of a biofiltration system can be expensive, involving the construction of a biofilter bed, provision of control system, and ongoing operational and maintenance cost. Limited pollutant removal capacity. Biofilter may have limited capacity to remove high concentrations of pollutant and their performance can decline over time as the microbial population become saturated or inhibited. Space requirement. Biofilter require a significant amount of space which may be limitation in urban area with limited available rent. Noise and aesthetic concern. Biofilter often require fan and ductwork and they may generate noise and raise aesthetic concern especially in residential or commercial area. Limited application range. Biofilters are most effective for treating low to moderate concentration of specific pollutant. For high concentration or broad spectrum pollution control, other technology may be more suitable. Uncertain performance for some contaminant. Biofilters perform can vary depending on the specific pollutant and their concentrations, making it difficult to predict their effectiveness for certain applications. Case studies. First case studies biofiltration technique in Germany. 1955 biological methods were applied to treat odorous emission in low concentration in Germany. Pollution caused by volatile organic compound and other air pollutants like odorous compounds, organic and inorganic compound including nitrogen and sulfur containing compounds. Case studies to biofiltration technique in Netherlands. 1919 there are more than 500 biofilters operating in Netherlands at landfill site and vermicompost plant and sewage treatment plant. Case study 3 biofiltration technique in New Delhi. 2018 Gurudwara Rakabganj Sahib biotech filter for cleaning polluted air have been installed in an open space on the Gurudwara premises. Environmental impact. Air pollution control. Biofilters are commonly used to treat air pollutant emitted from industrial process such as volatile organic compound and odorous compound. They can significantly reduce emission of these harmful substances, leading to improved air quality and reduced health risk for nearby communities. Energy efficiency. Compared to some traditional air and water treatment technology, biofiltration systems often consume less energy, making them more environment sustainable. They rely on natural process and microorganisms to degrade pollutant, reducing the need for energy intensive process. Future trend, emerging technology and innovation in biofiltration. First is nanotechnology. Nano-sized material and catalysts are being integrated into biofiltration system to enhance contaminant removal efficiency. These materials can absorb or catalyze the breakdown of pollutant, making biofiltration even more effective. Second is bioreactor. Advancement in bioreactor technology are improving the scalability and performance of biofiltration system. High-rate bioreactor membranes bioreactors and fluidized bed bioreactor are examples of innovation that can handle higher flow rate and concentration of contaminants. Third is genetic engineering. Genetic modification of microorganisms used in biofilter is an emerging area of research. By genetically engineering microbes, we can tailor them to efficiently degrade specific pollutant, increasing biofilter applicability. Hybrid system. Combining biofiltration with other treatment technology such as electrochemical process or advanced oxidation can create hybrid systems that tackle a broader range of contaminants effectively. Conclusion. Biofiltration offers a promising solution to address the growing concern of air pollution. Its advantages including being environment friendly, cost effective and sustainable make it a valuable tool in our fight for cleaner air. Biofiltration has a wide range of applications from industrial setting to improving indoor air quality and wastewater treatment landfills.